Welcome to the next lecture. Uh, Today we will start formally digital communication part. So we will first see that what is the bridge from analog to digital communication. So there are some reasons, first of all, why we don't prefer analog communication, and why in modern world whatever communication we have, whether it is 4G, 5G, or the Wi-Fi, is mostly based on digital communication. So one of the reasons is that will be error performance. Okay, error performance, and the other reason is in the multiplexing issues. Okay, these two are better dealt in digital communication rather than in the analog mode. Now, what is the bridge from going analog to digital world? What is the doorway? So that you are actually expected that you must have studied it, but I will revise it briefly. It's called sampling theorem. Sampling and then quantization. Okay. So without wasting any time, let me directly come to the point, and I hope by now those of you who were not familiar earlier with basics of communication systems, they must have revised it. They can watch my other videos of communication system which are for BTech, but they can watch those basic videos on AM, and I'm going to upload some subsequent videos on FM also. Now we assume that we have a signal represented by g of t, and this signal is band limited. Okay, what do you mean by band limited? Its bandwidth is finite. That is, if we draw the Fourier transform, see, the information about bandwidth is captured via Fourier transform. So if we see the Fourier transform, it looks like something like this. Okay, and it is band limited to b hertz. B hertz. Okay, what does it mean? So it means that if you see the Fourier transform, this will be 2 pi b, this will be minus 2 pi b. Okay, this is Fourier transform g of omega versus omega, angular frequency. If you plot g of f, that is the frequency, then we can write here b and minus b. This is what it means to be band limited. Okay, and now let's see that in time domain it can be anything. Suppose I draw the arbitrary something like this. Suppose this is your time domain representation of this signal g of t. So this is the analog signal, right? Analog signal actually means it can take any value. There is no restriction on the value. The value which it can take belongs to the set of all real numbers, right? It can take any value. It can take root 2, it can take e, it can take 1.111, whatever you think of value, this signal can take. There are a lot of issues, and also this is let me write it here. So this g of t is continuous time analog signal. Okay, that is, it is defined at every point of time. There is no, so if I say that at t is equal to 0, suppose it starts at t is equal to 0, you cannot say what is the next time interval. If you say 10 to the power minus 9, I can say the signal also exists as 10 to the power minus 99. Someone can say it exists also at 10 to the power minus 99999, so on and so forth. So theoretically speaking, this signal is defined at all the time. It's called continuous time signal. So there are several issues. We cannot store such signals practically, right? You need infinite memory. You see, from time point of view, time domain point of view, you need to store. Suppose if you are transmitting this signal from 0 to even suppose this is 1 second, but still, how many values you have to store? Infinite. In fact, it is actually uncountably infinite. We cannot store it practically. Okay, so practically storage of a continuous time signal is not possible. Now, one is the possibility, but there is a strange result that it is not also necessary. So what should we do? We should take samples. Take samples of this g of t. Okay, so what does that mean? Suppose if you take this signal, now let me take the samples with red color. So I will take, suppose, this sample, this sample, this sample, this sample. I am taking equally spaced samples, and I will just draw these lines so that I can get the time interval when I am taking it, and the gap between each sample we represent with ts. Okay, then this sampled signal can be is simply this one. Sorry. Now the question is, if you transmit this signal, the sampled one, from these samples, will we be able to recover the original signal? Let's see a mathematical way of recovering the original signal. You may say that I will join these points, extrapolation you can say. So I can join these points via straight lines. Okay, so this somehow resembles the original signal, but since these are straight lines, there is some error also. Now, how to reduce the error? You may say that, okay, we will take more samples. I will take extra samples in between. The more samples you take, so the better you can reconstruct. We call it reconstructing the signal from the samples. You can reconstruct the signal in a better way with less errors. So in earlier 20th century, Nyquist asked a fundamental question that is there a minimum number of samples such that if we take that much number, if we take only those number of samples, if we take those samples, then we can perfectly reconstruct the original signal. Okay, our answer is yes, and let's see how. First of all, we have to see that how we can mathematically realize the sampling operation. Okay, let's come back here. Let's discuss about just if we want to take one sample. Suppose this is t is equal to 0, and I want to take one sample. See, this is g of t, and what will be the sample at t is equal to 0? That is g of 0. Suppose I just want this one sample at t is equal to 0. What should I do mathematically? So we will need a mathematical function called impulse function. Impulse function, as you might be knowing, that it is infinite for t is equal to 0, it is 0 for t not equal to 0, but it has one strange property. So one is obvious property that its area should be 1, and also that g of t delta t from minus infinity to infinity dt is equal to g of 0. Okay, this is another property of impulse function. And if you see this property, what this does, this operation does, it samples g of t at t is equal to 0. Now suppose you want a sample at this time interval, suppose ts. So what should you do? You should do g of t delta of t minus ts and integrate it dt. You will get g of ts. Now this way you took one sample. Now what if I would like to take another sample at 2 ts? So what will you do? So you will basically, so now this integral operation, okay, we will just omit it. I will just multiply. So I will just do g of t delta of t minus ts, then plus g of t delta of t minus 2ts. Now just imagine if I want all these samples. This is now minus ts, minus 2ts, 3ts, so on and so forth. Then the sampled signal can be represented as, we will multiply this g of t with this delta of t minus 3ts, it is coming from infinity, plus delta of t minus 2ts plus delta of t minus ts plus delta of t plus delta of t plus ts, so on and so forth. So this is called impulse train. So if I plot it, let me plot it here, impulse train, it looks like this. And I represent it by delta ts of t. Why? Because these samples are separated by, these impulses are separated by this ts, which is a sampling interval actually. And this is periodic function. And as you might have done in your BTech, that any periodic function can be represented in terms of Fourier series. Okay, something like this, of this form: an cos of n omega naught t plus summation bn sine of n omega naught t. So you can find an and bn, which depends upon the n, and we can then expand any periodic function in terms of cos and sine. Now see the sampled this sampled signal can then be represented as g of t bar, which is equal to g of t delta ts of t, okay, and which can be written as summation g of nts delta of t minus nts, okay, overall n. Because when you are multiplying this with the impulse train, so only samples at n is equal to 0, n is equal to 1, n is equal to 2, only those samples will remain. Okay, now look at now this was your signal, suppose g of t, and this is Fourier transform, suppose it is this shape, band limited, of course, g of omega, suppose its amplitude is a, okay, and now we multiplied it with impulse function, and what we got in time domain, we will get this one. Okay, so this is your g hat of t. Now we will not derive it, we can try it at our places, that the Fourier series of delta ts of t, because it is a periodic function, so its Fourier series is this 1 over ts 1 plus twice cos omega s t plus twice cos 2 omega s t plus twice cos 3 omega s t, so on and so forth, where this omega s is 2 pi by ts, which is 2 pi of fs. So fs is equal to 1 by ts is the sampling frequency. Okay, now what will be the sampled signal then? G hat of t will be g of t times delta ts of t. So this will be equal to 1 over ts g of t plus 2 times g of t cos omega s t plus 2 times g of t cos 2 omega s t, so on and so forth. Now how does it look like? Again, I recall now a property of Fourier transform. If g of t has a Fourier transform g of omega, then g of t cos n omega st will have Fourier transform of 1 over 2 g of omega plus omega s plus g of omega minus omega s. Okay, this is the shifting property, which all of you must be knowing. Okay, now if you look at this g hat of t here, its Fourier transform will be, so g hat of t, its Fourier transform. So the first term is 1 over ts, that will remain as it is. So here is g of t, it becomes g of omega, right, plus then there is g of t cos of omega st, 2 into, so we'll use this formula, 1 over 2 g of omega plus omega s plus g of omega minus omega s plus similarly 2 times, then there is g of t cos of 2 omega st, so g of omega plus 2 omega s plus g of omega minus 2 omega s, so on and so forth. So this 2 and 2 will get cancelled throughout, so it will be 1 by ts g of omega plus g of omega plus omega s plus g of omega minus omega s plus g of omega plus 2 omega s plus g of omega minus 2 omega s plus g of omega plus 3 omega s plus g of omega minus 3 omega s, so on and so forth, right? So I can write in short 1 by ts g of omega minus n omega s summation n is equal to minus infinity to infinity. This I can write short, okay, and from minus infinity to infinity you will see all the terms will be covered. and I can write this as g bar of omega. G bar of omega. So this sampled signal has Fourier transform g bar of omega given by this thing. How will it look like? So let me go back to this figure. So this was a sample signal, its Fourier transform will be now. So we have, see, look at it carefully. One term is g of omega, so that is the Fourier transform of the original signal. That will be here. And then there are other terms, right? G of omega plus omega s, correspondingly omega minus omega s, omega plus 2 omega s. So we can draw it is a periodic Fourier transform. This okay, so this is omega s, this is 2 omega s, so on and so forth. This is minus omega s minus 2 omega s. So this is g bar of omega. Okay, now I want to reconstruct. Now see here, look at this carefully. G of t is a time domain signal. Its Fourier transform is g of omega. G of omega is in frequency domain. It contains all the information about the time signal. If you know g of omega, it means you know g of t, and vice versa. Now the sampled signal is g bar of t. Its Fourier transform is capital G bar of omega. So if you now what is the thing? So we want to reconstruct g of t from g bar of t. In frequency domain, it is equivalent to reconstructing g of omega from g bar of omega. So we can frame this problem like this. So here are the possible ways that g omega may look like. This is one possibility, g bar of omega. So this will be omega s, 2 omega s minus omega s minus 2 omega s. The other possibility is you have sampled in such a way that they overlap. So this will be omega s, this will be 2 omega s, right? Now what is the goal? If you see the scenario 1, the goal is we want to get back this g of omega. So we can put here a low pass filter, then we will get back g of omega. Okay, but if it is scenario 2, where will you put low pass filter? If you put like this, you will not get original g of omega, you will get something like this. You will get this, right? This is not g of omega, right? It's not g of omega. What is the first case, tight case? That is, this is g of omega. Then as its spectrum ends, starts another one. Okay, so this is g bar of omega. This is omega s, 2 omega s minus omega s minus 2 omega s. Okay, now look at various things, how we can compute that, how we should sample it. See, all of you know that this point is 2 pi of p, this is minus 2 pi of p. Now look at this, this is 2 pi of b, this is minus, sorry, this is minus 2 pi of p, and this total is 4 pi b. Similarly, this length is also of 4 pi b. Okay, now look at this tight scenario. So how much is this length? This is 2 pi b plus 2 pi b, this is also 4 pi b. So what you observe here is that this omega s should be greater than 4 pi b for these spectra not to overlap, right? Because if you see the scenario number 2, here actually, you know, this gap is less than 4 pi b, right? That is why overlap is happening. And if overlap happens, you can't put a filter. Now in this case, in the third scenario, the tight case, you can put an ideal filter like this, right? And you can get back g of omega. Although I will tell you later on that this ideal filter is difficult to design, but we can. So hence the minimum angular frequency required for sampling will be omega s should be at least 4 pi b, or I can write as 2 pi fs should be greater than 4 pi b, or fs should be greater than 2b, right? Sorry. So the minimum sampling frequency fs is equal to 2b, and this is called Nyquist rate or Nyquist sampling frequency. If you sample at a rate less than fs, you will not be able to reconstruct the signal back, okay, because then there will be overlap. So this is the basic essence of sampling theorem. And further, ts, which is 1 over fs 1 over 2b, is called Nyquist interval. Okay, now in subsequent lecture we will study the quantization, the next step. This is the first step for going into the digital world. We just have from continuous time we have moved to discrete time, then we will study the quantization process also.